The big question that we are going to address in this video is why are non-terminating, non-repeating decimal numbers irrational? And to investigate this question, we're going to take a sort of reverse approach. That is, instead of taking a non-terminating, non-repeating decimal number and showing that it has to be irrational, we are going to show that if you have a rational number that results in a non-terminating decimal, that decimal has to be a repeating decimal. And I should mention right now that we will not be doing a formal proof of this result here. That is, we will not be showing that it's true for all cases. Instead, we're going to take a couple of examples and show that this result is true for them. And then hopefully you can take the ideas seen here and see that yes, indeed, this result must be true for all cases. So here we go. Let's start with a rational number that results in a non-terminating decimal. I'll use 125 elevenths. So we do indeed have a rational number here. We have an integer over an integer. And we'll just quickly confirm with a calculator that this rational number results in a non-terminating decimal. So 125 divided by 11 gives us 11.363636 and so on. So definitely a non-terminating decimal. So let's see why we get a repeating decimal here. And to write this rational number in decimal form, I'm going to use the long division algorithm. So hopefully you're familiar with that algorithm. If not, perhaps you can use a different method to show the same result. So here we go. We are dividing 11 into 125. And of course, the long division algorithm is all about place values. So we start by dividing 11 into 12, and that goes in one time. And then we follow the algorithm, and the next step is to multiply 1 by 11, and that gives us 11. And then we do 12 minus 11, which gives us 1. And the next step in the algorithm is to bring down this 5, and that gives us 15. And then we repeat the process. 15 divided by 11, well, 11 goes into 15 one time, and 1 times 11 is 11. And if we subtract 15 minus 11, we get 4. Now to continue the algorithm, we need more digits up here in the dividend. We can easily get them by writing 0.0, which doesn't change the value. That's still 125 that we're dividing into. But now we can bring down this 0 to get 40. Of course, we must add a decimal up here in our quotient. Moving forward, 40 divided by 11, well, 11 goes into 40 3 times. And 3 times 11 is 33. 40 minus 33 gives us 7. And again, we can add a 0 here after the decimal. It doesn't change the value of that 125, but now we can bring down that 0, giving us 70. 11 goes into 76 full times, and 6 times 11 is 66. At this point, we have 70 minus 66, which is 4. And we can bring down another 0. I want to draw your attention to something really important here. We've been here before. If you look right here, we were at a step where we had 40, and we figured out how many times 11 went into 40, and it gave us 3, and so on. Well, we're at the exact same spot right now. We have a 40, and 11 goes into 40 3 full times. 3 times 11 is 33. 40 minus 33 is 7. Notice we are just repeating this all over again. And if we continue to do this, we're going to get the same steps over and over and over again, which is why we end up with a repeating decimal up here. So let's just do a little bit more to show you why that happens. There's the 0. We can bring that down. 11 goes into 76 full times. 6 times 11 is 66. And 70 minus 66 is 4. Again, we can bring down a 0. And there it is. Again, we're getting that 40. So you can quickly see that as long as we keep repeating this process, we will keep getting the same values up here. That is 3, 6, 3, 6, and so on. So that's why we get a repeating decimal. And I'll just show you one more example where that repeating pattern consists of more digits. Let's try 853 over 7. So we'll do again a quick check with our calculator here. 853 divided by 7, does that give us a non-terminating decimal? Yes, and as we can see indicated by this line here, we have a repeating decimal. So let's take a look at why that happens. Why do we end up with a repeating non-terminating decimal? Here we go. We're going to do 7 into 853. All right. Starting with how many times does 7 go into 8? Well, it goes in 1 time. 1 times 7 is 7. Subtracting gives us 1. And we can bring down that 5. 7 goes into 15 twice. 2 times 7 is 14. And we subtract to get 1. And now we bring down that 3, just following the long division algorithm. 7 goes into 13 just 1 full time. 1 times 7 is 7. And 13 minus 7 is 6. And now we have to start introducing some zeros after the decimal. Bring that 0 down, we get 60. 7 goes into 68 full times, and don't forget to put the decimal up there in the quotient. 8 times 7 is 56. Subtracting gives us 4. Bring down another 0. 7 goes into 40. What's that? 5 times. 5 times 7 is 35. And 40 minus 35 is 5. So it doesn't look like we've repeated the process here yet, but it's just a matter of time before we hit the same numbers again. So let's keep going. We'll bring down another 0, and 7 goes into 57 times. 7 times 7 is 49. Subtracting, 50 minus 49 is 1, and we'll bring down another 0. Still not seeing that pattern repeat yet. Just give it a little more time. 7 goes into 10 1 time. 1 times 7 is 7. 10 minus 7 is 3. Bring down another 0, still not repeating. 7 goes into 34 full times. 4 times 7 is 28. 30 minus 28 is 2. Bring down another 0. 7 goes into 22 full times. 2 times 7 is 14. And 20 minus 14 is 6. Look what's happening now. We're going to get that repeating. So bring down another 0. There's our 60, and 7 goes into 68 full times. 8 times 7 is 56, and 60 minus 56 is 4. And I'm not going to go much further because you can imagine as we continue going on here, we will be getting all of this over again, which means that this pattern here is going to keep repeating. So there it is, a couple of examples to show you why if you have a rational number that results in a non-terminating decimal, that decimal has to be a repeating decimal. And as a result, if you have a non-terminating, non-repeating decimal, it did not come from a rational number, so therefore it must be irrational.